Thanks all for coming out here. I just wanted to share a little bit about my journey in getting here. So yesterday morning, I woke up with an extreme pain in my back, one I'd never felt before in my entire life. And after an hour of dealing with that, ended up in the ER, and they discovered a kidney stone. So, and so if I collapse on stage and am screaming in pain, don't worry, I just have a kidney stone, so no worries there. All right, so my talk's titled Lessons Learned the Hard Way, Building a Global Decentralized Storage Network. So Storj has a mission to take advantage of unutilized capacity, including hard drives and bandwidth across the world. We're an open source platform, and our data is multi-region by default. We're able to build this network by anyone who has either Raspberry Pi or extra space in their data center. They can join in, and those different tree branches kind of represent different regions, and so as the data comes in, it is redundant. We're able to do this, like I said, multi-region included. Our availability, durability, and privacy is up to industry standards. We also have edge detection, and our costs are at least up to 80% cheaper than S3. So what I wanted to go through with you all today is just how Storj works, how we achieve all that, and then do a deeper dive into some of the architecture choices, such as Erasure Coding, how we deal with long tails and repair. And then I wanted to share kind of a success story of what happened in the silver lining of the Texas blackout in 2021, how our architecture performed there. And then finally, we'll dive deep into some of these lessons learned the hard way. So my name is Dan Willoughby. I'm a principal engineer at Storj. I studied computer engineering at University of Utah, but I quickly discovered that I enjoyed software much more than the circuitry. So I took a job in mobile development at Canvas, and then picked up distributed storage at Vivint, and then Crowd Storage, which is the circle, was a sister company spun out of Vivint, where we built an alternative to S3 for their video clip security footage. We scaled up to 300,000 devices, and we're writing 10 to 15 petabytes a month on that network. And then Crowd Storage was acquired by Storj, so that's where I am today. So collectively, I've been working on distributed network storage for about 6.5 years. So how does Storj work? At the base layer, we have storage node operators. These are the people with Raspberry Pis, or they have a data center with unutilized capacity. They can join our network. And then we, at Storj, build demand by creating applications. Uplink is similar to AWS CLI. You can create buckets, copy files in and out. But we also have an S3 compatibility layer, so you can use like the Boto Python library or the AWS CLI just fine. And then our satellites handles the logistics of the network. So they make a user-friendly interface for customers not familiar with CLI tools, and it also handles the payment to the storage node operators. The satellites also ensure that the data is durable and handle repair. So what does it look like when a file is uploaded? First, it is encrypted, and then it is split into, I think 80 pieces is what we use in production today. And then those 80 are distributed across the world. So those may land in Europe, the United States, or some in Asia. And the neat thing about Erasure Coding, and I'm sure most of you are familiar, but we'll dive a little deeper later, is we only need 29 of those pieces to reconstruct the file. And so we can lose up to 51 of those nodes and still be just fine. The segments come back, and you decrypt the data, and the customer can view the file. So I always like to show this demo of, if I can see my mouse, of a 4K 60 frames per second video playing on the network. So you can't really see the text over here, but it says 797 storage nodes are sharing a piece of this file. So when I hit play, hopefully the Wi-Fi cooperates. Yeah, so that all of those connections are being established, the data is being decrypted, decoded, and you can view it here. And of course, we can hop around and stream different sections of this video. All right, back to the slide. Whoops. All right, so how does that work? How can we serve that file? The base of the architecture is erasure coding. So important numbers, or the important letters to note from here on out is K, the minimum amount of pieces you need to reconstruct the file, and then N is just how many total pieces. And that has the buffer for if nodes go offline, and also how we handle repair, which we'll dive in deeper later as well. So I've lost my cursor. Here we go. So for an example of erasure coding, this has a K of 4, the minimum, and 8 total pieces. So the blue represents the original file just split into 4 pieces, and the parity pieces can be used to reconstruct that file. So I can take any 4 of those, and I have that file. So here I have 2 parity pieces and 2 of the original, and then that works just fine. A little bit under the hood, here is the library that we use. It's open source on GitHub. I think Backblaze was a contributor to this library as well. And you notice I have this string. Oop. Uh-oh. What happened there? I don't know. I'm not sure if my screen timed out or something. So I have this string here called hey who. This is a string to check EC. And you notice the first 4 pieces is just that string, the actual string. So if I concat those together, I reconstruct the file. And then the parity pieces, it's printed out, it's just gibberish. That's how it can replace any of those 4 original. And so a little bit more like of the jargon here. If it was a 10 megabyte file, that would represent the 4 blue pieces and then 10 megabyte for the parity. So total data uploaded to the network would be 20 megabytes. We could also get even more durability by uploading an additional 10 or additional 4 parity pieces or 10 megabytes for a total of 30 megabytes in the network, and that would be an expansion factor of 3. So why do that? It turns out the unique circumstances of storage, each node operator is independent and either in their own house or in a separate data center. So we can actually get more durability without increasing our expansion factor. So you notice at the top of the chart, 2-4 encoding, the expansion factor is 2, and the durability there is 99.2. Oh, and I forgot to mention P here is representing, we calculate about 10% node churn. So 10 of the nodes can go offline in this diagram. So jumping to the middle there, 816 encoding, still an expansion factor of 2, but we're now at 99.99 durability. And then 2040, which is what we used for a majority of my work at crowd storage, the durability jumps to 6 nines. And it just keeps getting more and more durable the more pieces you put into the network. But you don't have to upload actual more data. And I think that's kind of neat. All right, so now that we've kind of covered how erasure coding works, I wanted to dive deep into how the data is structured, how we keep track of everything. And in my mind, it's a cheese slicer, right? So you're just slicing cheese. And I have the affiliate link for this, so you can come and get that from me later. No, just kidding. But this cheese slicer is very specific, and that's how we do it at Storj. So the block of cheese represents the file, obviously, and then we break that into segments. So And then those segments are then broken into pieces, which are then broken into stripes. So why would we do this? Why would we complicate something that is pretty trivial? The reason is so that we can stream that video. So if you think of the file as a video, if we just broke that into two 64 megabyte chunks, encrypted the entire 64 megabyte file, and then sent that into the network and deduped it, per se, in order to view that file, we would have to download 64 megabytes and decrypt it and then show it to the customer. But since we don't own any of the hard drives that we store data on, it has to be encrypted, and that is fundamental to the architecture decisions. We have this thing called stripes, which is about 4K. I think it's about 4K, and we encrypt that, and then we erasure code it, and then we send a piece out to each separate node. And so I'll segue into some more diagrams here. So at the top layer, we have the bucket. It stores the file data, and in our satellites, it has metadata where these nodes are in the network. And then the physical data is sent to the storage nodes. So here, this file is broken into two segments, and a segment is typically 64 megabytes, but it can be larger. And then here's where we encrypt it, but like I said, we don't encrypt the entire 64 megabytes. We break it into about 4K, last I checked, into stripes. So each 4K is then encrypted, and it may be larger than 4K, I just don't remember. And those stripes then are erasure coded into those 80 pieces, and each is sent serially to the piece, and those are on storage nodes. So you can kind of think of the storage node as kind of just a file server. It just receives pieces or stripes and puts them in a piece and puts them one after another. And so when we stream that video, if I need to just jump to the middle, I can just request an offset to that file, receive all those pieces, decode the erasure coding, and decrypt it, and I get that section of the file. Okay. And yeah, back to the original erasure coding, the first piece of those erasure coding would be on storage node A, the second on storage node B, and the third on storage node C. All right, so when we are actually uploading, we have to account for network conditions and malicious nodes. So we over-provision how many we upload to so that any number can drop off during the upload process. On the same thing on the way back, we over-provision who we download from so that it can account for either nodes that are malicious or those that are slow. And so just another illustration of what I'm talking about here. We need to have at least 80 pieces in the network, so over provisioning that to 110 storage nodes would, had we waited for all 110 nodes to complete the upload, it would take 20 seconds. But since we only needed 80, we can cut that short. And you see on the blue, cutting it short, the blue nodes make it so it only takes 2 seconds. So we get a 10x improvement simply by taking the fastest 80 storage nodes. And it actually works out in practice that there is always a number of fast nodes so that it's evenly distributed throughout the network. All right, so what happens when those nodes, either the person loses interest or they are a malicious node? We actually can repair that data. And so using a 2040 encoding here, we break down the repair thresholds into different colors. So we monitor the metadata, we check if the node is online, and we send them occasional health checks and consistency guarantees, and if the health count goes down into, say, the yellow range, there's only 27 healthy pieces, we will go download that file, reconstruct or split it up again, and then send it back to those nodes so that it is back to its 40 healthy pieces in the network. And of course, if an object ever gets to the red zone, that is all hands on deck. Make sure we can get that file before it disappears. All right, so the silver lining of the Texas blackout in 2021, we're all familiar with the Texas went offline and people lost their heating in their homes, all of that. Our first exposure to that was a great, huge amount of repair load. We weren't quite sure what was happening here. We had 1 million yellow objects, 100,000 orange, and 5,000 red. So we were a little bit panicked, not quite sure what was happening. So looking at the device graphs, we had at least 26,000 devices go offline, about 10% of our network. And so also not a good thing. And so someone who had just been reading the news lately kind of jokingly said, well, maybe the Texas is affecting the stats. And so we said, oh, interesting. And it turned out that indeed, triangulating all of the IP addresses on their location, the yellow there in Texas was denoting that we had a huge amount of offline reports in Texas. So we decided to pause repair, thinking that these would come online quite shortly later, so to avoid that cost. And sure enough, within a few days, all of our nodes came back online. So kind of takeaway from this is the system works. We had talked for years that in this hypothetical situation, if some country goes down or a large portion of our network goes down, we are still durable. And it was nice to not have to say that theoretically anymore. It actually happened and it worked. And so another neat thing was that the traffic was automatically diverted. Since we track nodes online in our selection pool, we could naturally upload the files to the various states in the United States or Europe without any extra work on our end. And you know, if something works without Texas, you know it works. All right, so this last portion of my talk is just what lessons we learned along the way that were done the hard way. And just to define that a little bit, I think a lesson the hard way is when customers are impacted negatively through downtime or corrupted data, or there's always those bugs that you're like, how in the world did we never find this like years later, right? And race conditions, either when you start over at a small, like a small scale, or at large scale, always uncovers things. And of course, I think we're all familiar with API mistakes that balloon into hacky things. So just to dive a little bit into that, going from the large scale 260,000 devices, we partnered with Western Digital to release a new distributed network on their MyCloud Home NAS platform. And so we went to about 3,000 devices at first. And interestingly enough, our repair system, the pieces would be on each separate storage nodes, but since the network was so small, when it repaired, it replaced piece 2 on storage node A, and we would just represent the pieces as a file with like some unique identification to that object, so it would actually replace that piece 0, which was not good. So after we learned that, at that small scale, we looked at our larger network, and it was about 4,000 objects out of 3.5 billion that were affected. So a very small scale on the, at large scale, not a very big bug, but on the small scale, it was happening more frequently. The next thing is, of course, the don't say this at a Storj developer conference, but we did have corrupted data that is definitely a hard lesson to learn. It was, again, not happening very often here. My coworker says, how in the world are we going to reproduce this? We've only found 7 out of 50 million plus objects. And so when these objects were not being able to repair, we could see in the logs, we would pull down all of the pieces, and just to visualize it, we mapped the data to this image. And the entire black squares are just nodes offline, so that doesn't necessarily denote corruption. But we were noticing these black stripes, you could say, and we weren't quite sure what was happening here. And well, we tried to reproduce it in our local dev environment where we could have like 20 storage nodes, and we just hammered it like crazy, trying to see what would happen. And we never saw these 0 bytes, these black sections show up locally. And so, like any good engineer, if you can't reproduce something, spin up a bunch of cloud nodes and add in some bash, right? And so we spun up 600 cloud nodes and made this for loop in bash to just upload like crazy. And then we had another bash script just monitor zeros, you can see, which is a neat thing in bash I didn't know of. And then if it detected anything, it would print that to a file. And sure enough, after doing that for a little bit, we were able to find where the bug was. So, like any good software engineering, we found this odd truncate part of the code and tried to track down the commit history, and no one actually said why we were truncating in this file. I even asked the original engineer, and he couldn't remember. And I asked the CTO and everybody, and we're like, why are we truncating here? And no one knew anything about that. But that was the source of the bug. So what the code essentially did was when we put one of those stripes to the network, it would stat the piece, and then it would add the data that it was sending on the offset, copy the bytes from the network to the disk, and then truncate to the desired length. And so just viewing the logs of this bug, the put would come in at offset, large number there, and then it would time out, or like approximately 2-minute gap. It would seem to time out, but it actually wasn't. So the client side would retry and put it again. That would succeed quickly, and then truncate, and then the next put would come in, and it would succeed. And then mysteriously and quite randomly, and our only guess is that some packets were stuck in the network that would finish that original put, and it would truncate back to where the first put would have finished. So essentially, we lost this data in the process. So the fix here was to remove truncate, and had we had more time to reproduce what was actually happening in the network with all those bytes and packets, that would have been a much more interesting thing to bring as a takeaway here, but that it is what it is. So I think I had a tiny demo prepared of the uplink CLI. So pretty much like any CLI tool, we have like access, make bucket, remove bucket, so I can type uplink make bucket, hello. And you have to remember how to use your own software. SJ instead of S3, make that bucket. And access denied. But anyway, I wasn't really going to show that, so that was ad hoc. Questions? What questions do you have? Yes? Yeah. so the question is how the metadata is structured and how we know where these nodes are. Is that correct? Yep, so in the Storj satellites, we use, I think it's CockroachDB to store the address, like a DNS lookup kind of thing, and then the other, yeah, I want to say just basically like a DNS, but in a different way, where the nodes check in using MTLS, and then they state where what their address is, and then we try to contact them. And once that handshake is proven, then we record that address in the metadata storage. Oh, right, yeah. Yeah, so how do you find where all the pieces of the metadata are? So the DNS is the one portion, the actual physical IP address, and then we, back to the bucket layer, it keeps track of what object is stored, and then there is each piece of that metadata has which node it is on currently. So a little bit of an overhead per object. The satellites store the metadata for where the pieces are in the network, yes. Yes, yep. Oh, okay. So is the question, how do you fetch the metadata from the vast network and then go contact the nodes? Okay, so the metadata is in the satellite. And so you would contact the satellite, get that metadata, and then go and then contact the storage nodes. And so our satellites are structured such that any community member can go and run their own, and the storage node operators opt into which satellites they want to be a part of. Thank you. Back here. Yeah, so the question is, the underlying blockchain is Ethereum. I think we have a storage utility token, and it's based on ERC20 on the Ethereum blockchain, yeah. They haven't switched over yet, but there is a countdown. So on our forms, we decided to pay our storage node operators in advance, just in case something goes wrong, but we don't anticipate any trouble. So I think those payments were sent out this Friday instead of on their regular schedule. Right here. Is there a big overhead of CPU for the Erasure Coding for the operators? Yeah, so the question is there an overhead on the CPU for the Erasure Coding on the nodes? And for the storage nodes, no, because you can think of the nodes as just like a file server. So they get an API request that says store these bytes at this offset at this file name. So the storage nodes are pretty, I want to say, not complex. And so the Erasure Coding happens client side. And so once those pieces are pulled down, then the client will then decrypt and decode the files. So not too intensive. Back there? Yes, so the question is, do you have a general idea what the market size is for this decentralized storage? I don't have specific numbers for you, but I do know that we've grown 100% since I've started working there. And the adoption is happening a lot more with blockchain mainnet snapshots, so they need to download their data quickly to get their stored or their blockchain nodes online faster. And then with our S3 compatibility layer, we're also seeing like media and entertainment adoption. We have a certain customer that previews videos for those in prison as kind of like a way for them to, it's a way to like, how do you say it? There's like religious videos or like learning content. And so that is one of our customers that is using Storj in that manner to view videos and stuff. Let's go here.
What do you think are the implications if one was stitching the data back to certain nodes come in, how do you come in compared to that question? So we go back to one steady based on all.
Okay, so I think the question is, how do you deal with the high churn rate of nodes? Okay. So part of dealing with that is the erasure coding being 2980. So there's that 3x expansion factor is one way to deal with it, having redundancy built in. The second part is an incentive mechanism, and the details are in the white paper, but I believe the storage nodes get a percentage of their payment for like this trial period until they are proven that they're not malicious or they're well behaved, and then they retroactively get that full payment at some like 3 months or a year. I don't quite remember. So yeah, again.
What is the ballpark estimate of the bandwidth overhead per node basis for like 1 unit of data? Communication channel.
Yeah, so the question is, what is the overhead bandwidth for the nodes to communicate with our network? Since the nodes really just receive the pieces, the overhead for them isn't very much. Where we see the overhead is the metadata on our satellites, and then we actually have algorithms that I was working on where we only fetch, say, a 2040 encoding. We only fetch 20 nodes for a certain amount of time and then hot replace it in with a different one. And so we were able to get that overhead much lower. I think today we overfetch, and we are thinking of switching in with that more robust algorithm to bring that overutilization down. Over here.
It sounds counterintuitive to me. Back in like probability classes at high school, we were basically told or taught that as you increase the number of units, right, the probability of failure should go up. Because your chart where you showed the durability was going up as you sliced it. I know you carried more redundancy, but it has to be an offsetting factor as you use, as the n goes, not the n, but k goes up, as the number of units you depend on to gather a file together goes up, your durability should go down as well, right?
Yeah, so the question I think was about that slide where we were saying the durability goes up without increasing the expansion factor, and you're saying that the probabilities of that happening seem to be in conflict? Is that?
Yeah, is there a paper that you can point to where that
Yes.
durability math exists?
Yeah, so in the white paper, we used, they state what model they used to calculate that node churn, and the actual name escapes me what research paper they built it on, but yeah, you can read in the white paper how we deal with that.
And just a quick follow-up question. If, let's say, I mean, these are like people like us who are
Okay, yeah, so the question is, if anyone can join your network, how do you have SLAs? How do you ensure performance and availability? A lot of it comes down to the erasure coding, that over-provisioning of those pieces in the network. We're able to lose up to 51 of the nodes at any given time and still be able to reconstitute that file and re-upload it. I mean, that worst case, right, is it gets down to 29. The other mechanism is the storage node operator is incentivized to keep it online based on payment with the utility token. Back here? Yes. So the question is, do you monitor the nodes? And on this slide here. Yeah, so the question was, what happens if like the availability of nodes goes down? How do you keep the data durable? Is that correct? Okay, so. Yes. So in this, yeah. So if any number of nodes, like say 10, go offline, we would detect that in our repair system. So it monitors which nodes are online, and if it gets to one of these thresholds, say like the yellow, 12 of the nodes have gone offline. We would then pull that net object out of the network, re-encode it, and then distribute it back to 40 nodes, so it's completely healthy. Well, awesome. Oh, one more here. Nope. Okay. Appreciate everyone coming out.